Introduce our final speaker for this session before lunch. This is Anthony Scopatz, who will be blinking his screen and talking about his about XDress, his type checker.
Hi, thanks, Matt. Today I'm going to be talking to you about a code called XDress, or XDress if you need to use the name in a professional environment. Which is kind of fitting. My name is Anthony Scopatz, and I've been around. So, let's dive right in. So, what is XDress? At its core, XDress is basically a bunch of code generators wrapped around or built on top of a dynamic type system, and we'll talk about what that is in a moment here. And so the motivation for this is that I have a lot of projects and I absolutely require first-class C++ support. The other thing is that I want the type system itself to be dynamic. I want to be able to go in there and modify it. This is different even during runtime. So this is different than something like Swig, right? Or where it might be possible, but it's definitely difficult. And the other requirement that I had and still have is that I want a multitude of front ends. So I don't want just one code generator. I want to be able to take the same bit of code that I'm wrapping and produce different front ends. And so I have a plugin system that we might get to that it really enables that. So what's the XDress workflow? Well, there are some external parsers, and then those optionally get fed into an API finder, so something that discovers the API elements that you're looking to wrap. Then that goes into an abstract syntax tree visitor, which describes the code, describes the API that you're looking at. And then finally, that gets fed off into a series of code generators. And a couple of them are actually included in the XDress core, and we'll go into what those do in great detail in the second half of the talk. Okay, so what isn't XDress? This is a probably more important question. Well, it's not a parser because that's hard and annoying. It's not a compiler because I don't care about the architecture. And it's certainly not a build system because that's really, really annoying. Okay, so what do I mean by a type system in a code generation context? Well, since we're not doing any parsing or compiling, that's someone else's problem. We don't actually have to worry about the size of the types, right? So that's nice. That basically means that the type system is a nice, clean way to spell types, okay? Not the actual types themselves. And what a type is in the type system is it's composed of these immutable Python types. So string, tuple, int, and then this custom type matcher, which I might mention in the future, which really took a lot of inspiration from the regular expression module, although in a very limited way. And since it's immutable, right, you can use them as keys in a dictionary, which is something that you might want to do with a type when you're doing code generation. So, just sort of a brief introduction or diversion into like what kind of types do we actually support? Well, we support base or primitive types. There's this other thing called dependent types, and there's another type, or kind of type, called refinement types. So the base types, these are kind of what you would expect, right? These are the things that we're used to dealing with a lot in NumPy, etc. So, you know, bools and characters and static length strings and floats and all and ints and everything else. It turns out any compound type of these, like structs and classes and things on the C or C++ level, also kind of fall into this primitive or base type category. Okay. Dependent types are another kind of type, and they're parameterized types based on some other value or another type, right? This is very, very much equivalent to C++ template types. It's the same sort of idea, right? So if you want to wrap C++ code, you have to have a type system that handles dependent types, which we do. And they tend to be spelled with tuples. So here's a couple of examples. If you want a set of strings, right, it's just you have some set dependent type, and then its template parameters come after it in the tuple. Or if you have a map of int and double, you get map int32 float 64. Not too difficult, I hope. Refined types are another type, and basically they say, aha, I have some other type out there. I'm going to determine some subset of that type that I want to take and give that a special name. So really what you have is you have the type name, the super type name, and a predicate, which is either a function or something else. It's typically a function. So some examples, all even numbers, all even integers are a refinement of the integers. It's pretty easy. Similarly, all strings that start with A are a subset of all strings, right? So they're a refinement type. And then going further, the set of strings, awesome as Anthony, is a refinement of A strings. I don't know who wrote these slides. No idea. These are also spelled with either just their string name or a tuple of the type name and the super type name. So for even integers, you can either call them even int or a tuple of int32 even int. We'll get to the code generation cool stuff here in a moment here. You can combine these, of course, right? Because that's something that you need to be able to do, right? So these nest and layer into one another and compose well. So say you have some range type which takes a type as an argument and then the range of values it goes from. Well, here you might have a range that's of integers from 1 to 42, and that's how you would spell it, just with a tuple right out. This has 3 template arguments. If you want an even int range, right, using our even integer type from before, you can instead put in the even int tuple right there. And then right down at the bottom, we have a map from even integers to a range of even integers. All right. And there's a lot more, actually. What I've shown you is kind of the highest level of the type system. It's really the shorthand that I expect users and developers to write in, largely because there's a canonical form that's much more complicated. And that's what, as someone who's doing code generation, you want to make sure that your type is your type. So you get input from the user and you pass it through this canonical form function. And that does a lot of things like resolving aliases, for instance, right? There's also a bunch of standard types that are higher level refined and dependent types that are just built into the type system. More can be added. I'm not opposed to that. And then there's this type matcher class where you can replace any portion of the type with sort of this singleton match any, and you can check whether another type is an instance of some pattern that you've defined. Okay, now on to sort of the meat and the dinner of the talk here, and into the code generations part. Okay, so if you remember the workflow diagram that I had at the beginning, the one step was to produce these descriptions of API elements. And so roughly speaking, we have variables and functions and classes / structs. And we want to produce idiomatic Python wrappers. And the main way we do that is through Cython right now. But to separate those concerns, you generate these dictionaries of description. So here's a dictionary that describes a class called Brienne, has parents and namespace, etc. This class has some constructors and a method and a single member variable on it as well. And it has a place for docstrings, etc. These are all published on the website. So you can go look at what the fields of these dictionaries are like. Okay, so now to walk you through a very small toy example of what XDress does, and I'll point out what you actually have to do. So say you have some bit of code, right? This is for wrapping large code libraries, so this is pretty small. But say you have some C++ code where you've got a namespace, Hoover, and in it you just have a class A, which has a single member variable and a single member function, A and power on that, and it has some implementation. All you have to do to wrap this is to generate Cython wrappers is you just have to write a special XDress RC file, And this is all that goes in it. This is exactly what you write. You say what the package is, you say where it lives, you say what the target package is, and where you want your like build temporary files to go, because this does a lot of caching to speed up the Crossdress runtime. And then you say what API elements you want to wrap. So here we have a classes. You say there's an A class in the Hoover file, or in the Hoover files. And then you simply run it, run and build. I cut off the build text here, but it tells you, aha, I'm looking for API names. I'm not finding any. I'm going to just describe the classes you told me to describe, and then I'm going to generate some C, C++ wrappers using Cython. So that's it, like maybe 5 lines or something. And then what does it give you at the end of the day? Well, it generates a bunch of Cython files, including a wrapper, C underscore CPP underscore Hoover.pxd, as well as a pxd file for this. And then this is the Cython implementation. So this is very similar to something that you might write in Cython, where you have your constructor. It's generating a new C++ instance of that class. Frees it if you tell it to free. It exposes the member variables as properties, which is what you'd expect, doing the appropriate typecasting and conversion. This gets much more complicated if you have more complicated types, right? And then it wraps this, this method call. If you had more than one function signature, the dispatch here, I might show you later if I have some time, because this expands a lot and gets crazier. Also, I should go back to this slide very quickly and just mention that here in these function signatures and everything, you're using the values from the type system, right? So you know what those values are. That's how this communication happens. Okay, and then the type system has methods for saying if I have this type, write it out as a Cython type, these various forms. Okay, so if you have that, well, does it actually work? And the answer is yes, right? So here, we're just importing the class from the module and making an instance and setting some values and running the code, and everything works. And this just happens very seamlessly. Okay, what's my time, Matt? 8 minutes, okay. Okay, so I will just go through this kind of quickly then. So say you have a function pointer that lives on a C struct. This is also handled nicely. I wrote a little extra function here to provide a direct C callback rather than going through the generation API. This also demonstrates that you can just stick in code to it if you want. And the nice thing here is that if you write a function in Python, you can then assign that as this function pointer and then even call it from C, right? All of that is handled automatically, and it gives you the same result. And then if you delete the reference in Python to that object, there's still a reference retained on the underlying Cython implementation, and so it still gets executed. And this works for even if you reassign and if you have 2 instances of the same thing, they don't overlap each other's function pointers and callbacks and everything. So it's kind of nice. It does what you would expect. Here's the method dispatch. I'll skip this unless I have time at the end. Okay, so the Cython generator is kind of one plugin or one thing that you can do with the type system. Another code generator that you can write are idiomatic wrappers to the standard library containers, right? So people like using map and set and vector and stuff. But you, from Python, want to view those as collections instances of those same objects. And you want to get those as views, not as copies. So what you do, here's a sort of larger example, but you just write out a bunch of types that you want generated, and it'll go ahead and make this standard library containers module here. I'm abbreviating it to const to just show you what I'm doing. So over the standard library map, you get all of these classes that represent maps of the various types, templated types. And here, right, this is a map from string to int. Everything's working correctly. You can assign into this and grab values back out, much like you'd expect. And you're not copying on each step, which is the key thing. And if you try, unlike a Python dictionary, if you try to assign into it something that isn't the right type, right here, we're a string to int and we're trying to assign a list, it'll tell you, oops, you did the wrong thing, buddy. Okay, and now for the really cool thing. Vectors in C++ are wrapped as NumPy views of the appropriate data type. So we generate NumPy D types for the type that you gave it. So here I'm just showing you that this is, the D type is there. If you wanted an NumPy array of standard strings, you can certainly do that. That sort of gets over this limitation of having statically length allocated strings. And if you want to see something sort of truly evil, you can even wrap these more compound types. So here we had a vector double, and we're wrapping that. And when you wrap that, you get an array of arrays of doubles. So these subarrays don't need to be the same length, much like they don't in C++. And I should note that as long as, right, all NumPy cares about is that the size of the type is constant, and that's true for any standard library or anything in C or C++. So this will even work on your classes that you write. If you want a vector of some custom class, and you have the wrapper for that class in XDress, it will know, or if you've exposed that to that class to the type system, it'll generate a D type for you of that class. And just to show you that that works, here's something kind of compound, right? You only live once. Here's a map of int vector pool. And if you initialize that, you can see that every element of this is just a map int vector pool, right? Because that's also in the type system. So this makes wrapping C++ code really, really nice and really, really easy and very fast and idiomatic in both languages, which is kind of key. And then to kind of wrap up here, if you want to have your own plugin, if you want to expose your own code generator, you just write a very simple plugin that implements this interface and stick something with the name XDress plugin somewhere in some module. And then the whole architecture that you've seen, you have access to. You have access to the type system, you have access to the run control file, you have access to all the descriptions that were generated, you have access to all the parsers that were used. And you can sort of say what options you want. Everything in the run control is a valid parameter in your actual run control file. We just use argparse, so you can actually modify the command line interface this way if you want to be able to change the user to be able to change options on the command line. And then there's a setup, execute, teardown, and debugging report method that all happen as well. It's very, very simple, and it's clean, and I'm really happy with it. Because the idea here, once again, is that XDress enables you to write your own code generators on top of this type system that I think is pretty dang powerful. Since I have, I guess, one more minute, I will show you just how dispatch works very quickly. So say you have some function, so you have some function on in a module somewhere. The first thing that it tries to do is it actually tries to do dispatch very similarly to how C or C++ would do by matching the types. And then it will go into sort of duck type mode and try every signature that you provided and see if it fails. So, and that's the work to date, and we're pretty happy. I think there's a lot of ways to go with this. Some cool ideas that I had was the reason that we didn't use Clang here, if you're wondering, is that the Clang AST Python bindings don't give you template arguments, just super annoying. But you could actually use XDress to wrap, in its current state, to wrap the Clang AST C++ library, generate Python bindings, and then use those Python bindings as your parser for XDress. Another thing that I haven't really explored that I think would be really cool is to create since the type system is so dynamic and allows you to throw predicate functions wherever the hell you want them, you can create a validation engine that isn't based on XML, which would be awesome. And then another thing that I was playing around with the week before is this SIA project, which of course SIA rot 5 is HDF, is to just wrap the entire HDF5 library with cross-dress. I got 98% of the way there, and then discovered some really, really annoying bugs in PyC parser that I'll have to get fixed before we can move on. So with that, I will take any of your questions. We have a mailing list and a website, so please come and give us. We're always looking for feedback. So.
We have time for a couple questions and then lunch.
Is there any plan to try to extend, just like try to integrate in maybe with setup tools? Because there's a lot of information you provide for that initial config file for the final step to build. Looks like a lot of the same information you provide to setup tools to distribute. That makes sense, maybe integrated into the setup.py.
So the question was whether we were going to try to integrate with setup.py and setup tools. That's an interesting idea. I hadn't really considered it. I would be 100% behind that if someone else wanted to implement it. Yeah, Matt. So the question is how to get the ecosystem to work better and to interoperate better. I think actually a lot of those ideas are really here in this talk, in that you want to make it easy to write views, right? It's not about doing copies and having this big memory overhead that's what kills you. This NumPy view concept, or this view concept, is actually really, really powerful, and it allows people, if you make it easy to have those views, it allows you to, in whatever language you're currently in, to maybe have a little decorator code around it, but it allows you to operate and write code in the way that's nice in that language. So, yeah, I guess that's what I would say.
Okay, thanks. Let's thank the speaker one more time.